The periodic table is a powerful map of all known elements, organizing them by fundamental patterns in their structure and behavior. In this video, you'll learn how it evolved, why its layout matters, and how trends reveal element properties. Before the modern table, chemists grouped elements using simple patterns. Dobereiner arranged elements into triads with similar properties and middle atomic masses. Newlands proposed octaves, noticing that every eighth element shared characteristics. These early systems were imperfect but revealed that elemental properties repeat in regular, predictable ways. Mendeleev organized elements mainly by atomic mass, but, crucially, left gaps where patterns suggested undiscovered elements should exist. He predicted their properties with surprising accuracy. When new elements were later found that matched his predictions, it strongly confirmed that elemental behavior follows an underlying periodic order. The modern periodic table is built on atomic number, the count of protons in an atom's nucleus. Modern periodic law states that elemental properties are periodic functions of atomic number. Arranged this way, elements form 7 horizontal periods and 18 vertical groups, where members of each group share similar chemical behavior. Atomic size changes predictably across the table. Moving down a group, atoms get larger because new electron shells are added. Moving left to right across a period, atoms usually get smaller, as increasing nuclear charge pulls electrons closer. Understanding these size trends helps explain bond lengths, reactivity, and how atoms pack together in solids. Metallic character describes how strongly an element behaves like a typical metal, easily losing electrons, conducting electricity, and forming positive ions. This character increases down a group and toward the left side of the table. Nonmetals, found toward the upper right, are less metallic, tending instead to gain electrons and form negative ions or covalent bonds. Some elements show diagonal relationships, where a light element in one group resembles a heavier element diagonally adjacent in the next period. For example, lithium shares behaviors with magnesium and beryllium with aluminum. These similarities arise from balancing effects of charge density, ionic size, and bonding tendencies, offering subtle clues about chemical behavior. The periodic table captures how elements relate through atomic number, size, metallic character, electronegativity, and even diagonal similarities. By recognizing these patterns, you can predict how unfamiliar elements might bond, react, and combine, turning the table into a practical toolkit for understanding chemical behavior across all of matter.